Hi, this is TheoryStation. I'm John Duggan, and this is the Rational Choice Modeling Program. This series is the one-dimensional policy choice model, and this is the third installment in the series. So last time I was going to talk about single-peakedness and majority voting. And the main thing was going to be to generalize the idea of Euclidean preferences. Well, I got carried away and didn't even get to that at all. So I'm going to pick up where I left off last time, right? So we have been imposing this one-dimensional structure and thinking about Euclidean profiles of preferences. That means each voter has an ideal point, and they just like alternatives that are closer to that ideal point. And then we had, that's a lot of structure, and we were able to get very sharp results about majority voting. We had the median voter theorem that said the majority preference relation, again, we were assuming an odd number of voters, distinct ideal points, but the majority preference relation coincides with the median voters. So the median voter's ideal point is a Condorcet winner. The majority preference relation is a weak order. And we've talked about Arrow's theorem and how this actually, because we're reducing the domain of possible preferences, we actually get a very positive result. The majority rule satisfies rationality, IA, Pareto, and no one is a dictator. So we got a lot out of that model. So one normal sort of activity in mathematical modeling is to, you impose some structure on the model, you get results out, but then you have to think, well, so how much do these results really depend on the structure that we're imposing? Are they robust? If the results would hold in a more general model, then, we typically, we want to be as general as possible, and we should, relax our assumptions and think about a more general model. Often what happens is we find that, we're imposing structure, we get results out. If we relax that structure that we're putting into the model, the results don't hold verbatim in the more general model. They hold in a relaxed form. So some essence of the results carries over, although the particulars might actually fade a little bit. And that's what we're going to see in this single-peakedness framework. Okay, so to begin with, let me define single-peakedness, and to do that, let me first go back to Euclidean preferences. All right, so suppose person I has Euclidean preferences with ideal point VI. All right, so that means if I draw a line representing the set of alternatives, their ideal point somewhere on that line. And if I were to graph a utility representation of that preference relation, I could use quadratic utility, and I would get something like this. That's pretty bad. Okay, or I could use that Euclidean utility, which gives me a kind of tent-shaped graph of the utility function. Either of those are valid representations, and that's fine. But one feature that pops out when you graph these utility functions is that they're symmetric about the ideal point, right? So with quadratic utility, we have this smooth curve, and the part to the right of the ideal point is really just a mirror image of the part to the left. Another way of saying that is if I take an x to the left of the ideal point and I take a y that's the same distance, then the utility from those alternatives is the same. Okay, we would say that these utility representations are symmetric about the ideal point. And what that means is that if two alternatives are the same distance from the voter's ideal point, then the voter is indifferent between them. Okay, that's just an obvious implication of Euclidean preferences. The voter only cares about distance, and therefore any utility representation of Euclidean preferences has to have this symmetry property. All right, but what about something like this? Suppose we have our set of alternatives, an axis for utility, and suppose that the utility function has this kind of form. And now I've purposely drawn this to be not symmetric around the ideal point, right? The utility drops off faster as we move to the right from the ideal point. It doesn't drop off as fast when we move to the left. Okay, so that would mean that this voter, there's something about pushing policy to the right of their ideal point that impacts them in a greater way. It just has more of an impact. Okay, pushing it to the left still hurts the voter, but just not as much. Okay. On the other hand, you could have another voter like voter J over here, and they might be the opposite. Maybe they, pushing policy to the left for them has more of an impact, and so their utility function is asymmetric around the ideal point, but in the opposite way. Okay. And I can keep drawing in curves here. What if I actually did one that's kind of wavy and like this, and there's voter K, let's say. Now that obviously, is different in another way, in that, this utility function is not concave. And compared to, if we push policy to the right for this voter and compare that to pushing it to the left, well, the comparison, at first moving to the left doesn't have as much impact, but then it has more, and then less, and then more. So anyway, what I'm getting at is a bigger family of preferences. They're not Euclidean, but still there's some aspects of Euclidean preferences that these have, right? Each voter has an ideal point. There's one policy or one alternative that's preferred to any other, right? For voter I, it's this point right here. And, as we push policy to one side, it makes the voter worse off. If we push policy to the other side, it also makes the voter worse off, but possibly not in a symmetric way. Okay, so these utility functions that I've drawn down here represent preferences that we're going to call single-peaked, but they are not Euclidean. Okay, so let's give a general definition of single-peakedness. So let's assume, I've already been doing it, but let's officially assume that the set of alternatives is a subset of the real line. Then we'll say a preference relation, PI, is single-peaked. If there exists an alternative, VI, and that's going to be the ideal point, such that three things hold. Okay. So one is that for any alternative not equal to the ideal point is strictly preferred to that alternative, right? It just means it's better than every other alternative. The second condition is that for any two alternatives, x and y, if x is less than y and y is less than the ideal point, then y is strictly preferred to x. Okay, so this is capturing the idea that if you push the alternative to one side, in this case, if you push it to the left of the ideal point, here's y, that's obviously worse than the ideal point, but now let's keep pushing it to x, right? That makes the voter worse off, okay? Moving from y to x makes the voter worse off. That's what condition 2 here says. And finally, the third condition is that for all x and y, if both alternatives are to the right of the ideal point with x less than y, then x is strictly preferred to y. Same idea, but now we're just pushing the alternative in the other direction. Okay, so if we start at the ideal point and go to x, obviously that's not as good for the voter. And if we keep pushing to y, that makes the voter worse off. Okay, so all right, that's the formal definition of single-peakedness. We've already seen examples of what a utility representation of a single-peaked preference relation would look like. Okay, if PI is single-peaked and if it has a utility representation, then it's going to be maximized at the ideal point. Okay, let's say there's some maximum utility up here. And then as we move to the left, the utility is going to drop, right? That's condition 2 here kicking in. And I should say, I usually draw nice continuous utility functions. It doesn't have to be continuous. We're not even assuming that. But we are assuming with single peak preferences, we're assuming if you keep moving to the left, the utility goes down. If you move to the right, the utility goes down as well, and we can do another let's not do it there. We can do it like this. We can do another discontinuity. But as we move to the right of the ideal point, the utility has to go down. Okay. So this is a utility representation of a single-peaked preference relation. It doesn't have to be continuous, doesn't have to be smooth. And what we're doing in this installment, we're not using any calculus, and there's just no need to impose that. Okay. All right, so that's the idea of single-peakedness. I should say, just an aside, not every single-peak preference relation has a utility representation. It's just a little mathematical tidbit, but if it does, it's going to have something like this structure here. All right, so that's a single-peak preference relation. We'll say a preference profile is single-peaked if each preference relation in the profile is single-peaked. Okay, so again, I think just to avoid, just to make things simple, and maybe I can say a little bit about what happens in the more general case, but let's assume that n is odd, and we'll focus on profiles with distinct ideal points. Okay, so again, we'll say M is a median voter. If we look at the set of voters with ideal points to the left, it's not a majority. And if we look at the set of voters with ideal points to the right, that is also not a majority. Okay? Under our assumptions, if n is odd, if the number of voters is odd, and if they all have distinct ideal points, then there's a unique median voter. And yeah, so we'll just keep using M to denote the median voter. Okay, so now what carries over here? So with Euclidean preferences, we proved the median voter theorem. Right? It said the majority preference relation is the same as the median voters. That does not hold in general when you just assume single-peakedness. Okay, and I'll just give an example of this. I'm going to take, how do I fit this in? Let's do, let's take 4 alternatives, A, B, C, and D. And they're on the line, right? So we're in the one-dimensional model. And I'm going to think about 3 voters, 1, 2, and 3. And their rankings of these 4 alternatives are going to be the following. So I have B, C, D, and A. I have C, B, A, and D. And I have D, C, B, and A. All right. So, you know, are these preferences single-peaked? Actually, let's just assume, so there's n equal 3. Let's just assume that these are all the alternatives, right? Just to make things concrete. But they're on the line, okay? This is perfectly permissible. So I have 4 alternatives on the line, 3 voters. These are the rankings of the voters. Let's make sure these preferences are single-peaked, right? Person 1 has an ideal point, right? B is preferred to every other alternative, okay? So that satisfies the first condition in the definition of single-peakedness. But now we have to make sure that the other 2 conditions hold. So, in fact, I want to graph utility here for person 1, and I'm going to just plot a point above B. Condition 2 says if you take 2 alternatives to the left of the ideal point, then the one further from the ideal point has to be worse. In this case, if we look at person 1, the ideal point is B, and there's only one alternative to the left. You can't find 2 alternatives to the left of the ideal point, and so condition 2 is actually vacuously satisfied. Okay. Condition 3 says if you take 2 alternatives to the right of the ideal point, and now we have 2, that the one furthest has to be worse. Okay, so for person 1, the ideal point is B. If we take C and D to the right of that ideal point, it better be that D is worse than C. Let's check. It is, right? C is better than D. So if I were going to plot utilities for these guys, I could do something like this and I'm going to put A's utility down here. Okay, so for person 1, this preference relation here is going to be single peaked, right? We have the ideal point B, and then as we move to the right, things get worse, and then A actually is worse than all of the other alternatives. All right, so I've plotted 4 different utilities here. I'm just assigning utilities to these alternatives in a way that represents the ranking, and that's all I needed to do. Let me just connect the dots, even though that's not really technically needed. It's going to help us see that utility function. All right, let's do the same thing now for person 2. Their ideal point is C, right? Now condition 3 is going to be vacuously satisfied because you cannot find 2 alternatives to the right of C. But you can find 2 alternatives to the left. There's B, and then A is even further to the left. So single-peakedness is going to tell us that for person 2, B has to be preferred to A, right? And if we look, it is. Person 2 prefers B to A. So if I were going to write in a utility function for person 2, I would have to give C the highest utility because that's their ideal point, and then B would be next, and then A, and then D would have to have a lower utility than the others. Okay. So that's one possible assignment of utilities that represents person 2's ranking, and you can see it has this single peak flavor to it, right? Let's do the same thing for person 3. So D is their ideal point. And then condition 3, vacuously satisfied. There are no alternatives to the right of D. But now condition 2 would say as we push alternatives to the left of D, they have to get worse and worse. So it better be that C is preferred to B and B is preferred to A, and let's check. That is the case. Okay, so that checks out. This preference profile is going to be single peaked. In fact, I don't know if I want to do, let's do up here. All right. Now, seemed like more work than it really was. This is a one-dimensional model. We have a single peak profile. If you look, though, you can see that they're not Euclidean preferences. In fact, there's no way to you can imagine moving B, C, and D around, trying to, if you move them around, maybe you could make these look Euclidean, but there's no way to do it, okay? And the reason is, if you look at the majority preference relation, I should take a step back here. So the ideal points are B, C, and D. And the way these are ordered on the line, B is to the left of C and C is to the left of D. There's a unique median voter here, and that is voter 2. All right, so in this case, M is equal to 2. With Euclidean preferences, the majority preference relation would have to be person 2's ranking, okay? But in this example, it's not. And the way to see that is if we focus in on alternatives A and D, okay? So person 2, the median voter, prefers A to D. But if we take a majority vote between A and D, person 1 and person 3 both prefer D. So we have, person 2 prefers A to D, but majority of voters prefer D to A, and so here this is a capital M. D beats A in a majority vote. So that shows us that with single peak preferences, we don't get the same really strong median voter theorem, okay? But we still get a median voter theorem. It's just a relaxed version of it, okay? So let me state that. So this is the median voter theorem. Single peaked version. All right, so we're going to assume, as usual, we're in the one-dimensional model, and n is odd. Let P1 to Pn be single peaked with distinct ideal points. All right, then, right, let M be the median voter. That's the standard notation we're using. Okay, then we can say two things. One is that the median voter's ideal point is a Condorcet winner. Okay, that means that it beats every other alternative. Okay, and two, the majority preference relation is a weak order. Okay, so you know, these we both got with the original median voter theorem where we assumed Euclidean preferences. These followed from the result. Okay, the median voter's ideal point was a Condorcet winner. The majority preference relation was a weak order, but there we were putting in more structure, and in fact, we showed that the majority preference relation was equal to the median voter's ranking. What we find out now is that the majority preference relation is a ranking, but it might not be the median voters. In the previous example, we saw that you know, the two can be in conflict. But by part one here, the majority ranking will still have the same top-ranked alternative. Okay, the ideal point of the median voter will still be majority preferred to everything else. All right, so so what we can do to prove this without, I don't want to be super pedantic about it, but for part one, what we would do is we would consider any alternative that's not, you know, that's distinct from the median voter's ideal point. Okay, so for example, if the median voter is here, we can consider X to the left. All right, so by definition, if we look at the voters to the left of the median voter, that's a minority. Okay. In fact, I should say, if we look at the voters to the left of that, there is not a majority of voters, right, to the left. So that means if we look at the other guys, so the median voter and anyone to the right, there's at least n over 2 of them. Okay. All right, so to repeat, by definition of the median, if we look at the voters to the left, that's not a majority. So then if we take the complement of that set, which means the median and anyone to the right, there have to be at least n over 2 people in that set, right, in that group. Now we're assuming n is odd, right? So n over 2 is not an integer. There cannot be exactly n over 2 people in this group, right? So what that means is that this inequality has to hold strictly. There has to be more than n over 2. There can't be exactly. And that means that that group is a majority, right? So again, if we look at the set of voters who are either the median voter or anyone to the right, that group is a majority. All right, so let me write that up here. Or I'll do it down here. All right, so note that if we look at the voters who are who have ideal points either equal to the median or, sorry, I didn't write that correctly. If we look at the voters with ideal points either equal to the median or to the right, there's at least n over 2 of them, but there cannot be exactly n over 2. So in fact, it's a majority. Now, all right, but notice we're assuming single-peakedness, right? So, so clearly the median voter prefers their ideal point to x. And anyone over here to the right. Remember, condition 2 in the definition of single-peakedness says if you push policies to the left, you make that guy worse and worse, right? So that means that x is worse than the median's ideal point. So, so for all voters who are to the right, of the median, then we must have VI. Then for all voters who are to the right of the median, we must have the median ideal point preferred to x. Okay, so then we have this, we have a group, it's a majority, they all prefer the median ideal point to x, and therefore the median's ideal point is majority preferred to x. This is a capital M here, right? Because x was just arbitrary, I mean, I chose x to the left of the median, but to the right, the same argument would work. We just have to use a symmetric version of it. Because x was arbitrary, we've shown that the median ideal point is strictly preferred to every other alternative, so it's a Condorcet winner. All right. Now, so for the second part of the theorem, we need to show that the majority preference relation is a weak order, which means that it's negatively transitive, right? Now, to do this, it's going to be helpful to define the weak majority preference relation. And we're going to just use the same convention as we use for individuals. We'll define the weak majority preference relation we'll use an R instead of a P. As follows. We say, you know, for any x and y, x is weakly majority preferred to y if and only if it's not the case that y is strictly majority preferred to x, right? So it's just the same convention that we've used in the basic rational choice model. This is just how we talk about a weak preference relation. Okay, so with that definition, I want to make 3 observations. Okay, so first, if suppose you have 2 alternatives, x and y. If either x is strictly majority preferred to y, or it's weakly majority preferred to y, then the number of people, if you look at the people who weakly prefer x to y, the number of those must be greater than n over 2. There must be a majority of them. All right, so why is that? So just imagine that all of the voters are just represented by this blob here, right? And here are the voters who weakly prefer x to y, and then everyone else is over here, right? They actually must strictly prefer y to x. Now, right, because you either you strictly prefer y to x, or you don't, in which case you weakly prefer x to y. So this is kind of a partition of the whole society into 2 groups, and well, if x beats y, then you know y doesn't beat x. So so this, if we look at this group here, the red group, there can't be a majority of those guys. All right, but now, right, so if x beats y, we know that there can't be a majority of people in that red group. But we're assuming that n is odd, and so we know that, n over 2 is not an integer, so there cannot be n over 2 of those people, right? So this inequality has to actually hold strictly. So there's less than half of all the voters in this red group, and that means that everyone else in the blue group must be a majority. Okay? It's just the same. If x is weakly preferred to y, then by definition y does not beat x. So in the red group, there's less than half of the voters, and so in the blue group, there's more than half. Okay, so what we've shown is that in either case, there must be a majority of voters who weakly prefer x to y. All right, so that's one observation that I want to make. The next one is that this is just, the next observation is just that the majority preference relation is negatively transitive if and only if the weak majority preference relation is transitive. Okay, that's just something that we proved in the general rational choice framework, and so that means I can focus my energies on showing that the weak majority preference relation is transitive. Last observation. And this is expanding on something that we talked about before. But if I have 3 alternatives on the line, so in the one-dimensional model, suppose I have 3 alternatives like A, B, and C. And suppose that the individuals have single peak preferences, then the middle alternative cannot be bottom ranked among those three alternatives for any voter. In fact, specifically what I want to say is that if you look at any voter, they have to prefer B to either A or C, right? Why is that? If your ideal point's at B, then obviously you prefer B to both. If you're over here to the left, you prefer B to C. If you're to the right, you prefer B to A. So the middle alternative is preferred to at least one of the other alternatives by any individual. Okay. All right. So that's just an implication of single-peakedness, and now we can go ahead and prove the second part of the theorem. All right. So we just have to prove that the weak majority preference relation is transitive. So let's consider any alternatives, A, B, and C, such that A is weakly majority preferred to B, and B is weakly majority preferred to C. And then we need to show that A is weakly majority preferred to C. Now, the way I'll prove this is a proof by contradiction, or it's really just a process of elimination. There's two possibilities. Either A is weakly majority preferred to C, which is what I want to show, or it's not weakly majority preferred to C, which means that C is strictly majority preferred to A, right? Those are the two possibilities. And what I need to do is show that the lower branch is impossible, right? I'll suppose that's true, and then I will follow a chain of implications that eventually leads at some inconsistency, which means that branch cannot hold. Okay, so for a proof by contradiction, we'll go down this lower branch and we'll suppose that C is strictly majority preferred to A. And all right, so C beats A. We'll suppose that. Obviously, if C beats A, then A cannot beat C, and so of course that means that C is weakly majority preferred to A as well. Okay, right? That's just saying A does not beat C. And that's implied, assuming that C beats A. All right, so what this means is that we have a cycle of weak majority preferences, right? If we were going to graph this weak majority preference relation, we are assuming that A is weakly majority preferred to B, and B is weakly majority preferred to C. And now we're going down this bottom branch, and there C is weakly majority preferred to A. There could be other arcs in this graph, but at least it contains these arcs. All right. So I'm going to show that that having a weak majority preference cycle like that contradicts this third observation here. All right, and we're going to use the first observation. All right. So, so I want to argue that there's some alternative. Well, let me put it this way. We have three alternatives, A, B, and C, on the line somewhere, on the real line. One of them is in the middle. I don't know if it's A or B or C, but whichever one it is, I'm going to argue that there's some voter who has that either at the bottom or tied at the bottom of these three alternatives. Right? That's inconsistent with this third observation. All right, so the way I'll argue that is technically, there are 3 cases, but they're all proved in the same way, right? So it might be that A is in the middle, or it might be that B is in the middle, or it might be that C is in the middle, okay? They're all proved in the same way, so let's pick case 1 and just see how that works. Right? If A is in the middle, single-peakedness means that, or it implies that for any voter, that voter must prefer A to either B or C, or maybe both, but at least one of those, right? Now, in case case 1, sorry, remember we have this weak majority cycle. We have a weakly majority preferred to B, weakly majority preferred to C, weakly majority preferred to A. Now, let's look at these 2 arcs. So in case 1, we have B, weakly majority preferred to C, weakly majority preferred to A. Since B is weakly majority preferred to A, since B is weakly majority preferred to C, that means that the number of people who weakly prefer B to C is greater than n over 2. It's a majority, okay? Since C is weakly majority preferred to A, that means the number of people who weakly prefer C to A is also greater than n over 2. It's a majority, okay? So that means that these 2 groups must overlap, right? If you have 2 majority groups, their intersection must contain at least one individual. There's some individual I, who's in the first group. So, they weakly prefer B to I, and they're in the second group, so they weakly prefer C to A, okay? Now, right, then for that, and there could be more than one person. I'm just saying there's at least one person in the intersection of those 2 groups. Let's pick one. Let's call that person I. And just directly, of course, they weakly prefer C to A. But also, remember, person I's preference relation is a weak order. That means that the strict preference relation for person I is negatively transitive. But of course, that implies that the weak preference relation for person I is transitive. Since they weakly prefer B to C and weakly prefer C to A, that means that they weakly prefer B to A as well. But that means here we have an individual who does not prefer A to C and does not prefer A to B. That violates single-peakedness, okay? Right, as we said, if an individual has single-peak preferences, then that middle alternative has to be strictly preferred to either the one on the left or the one on the right, or maybe both, but at least one of the two. Here we have an individual who does not strictly prefer A to C and does not strictly prefer A to B. That contradicts single-peakedness. And so in case 1, where A is the middle alternative, we see there's a contradiction. But the same argument works in case 2 and case 3, okay? All we're using is the fact that there's a weak majority preference cycle between these 3 alternatives. That is impossible when the individuals have single peak preferences, right? So here's what we've done. We've looked at, there's the 2 possibilities. A is weakly majority preferred to C, or C is strictly majority preferred to A. We followed this bottom branch and we said, well, there's these 3 possibilities. One is A is in the middle. And we just showed that that can't hold. The other possibility is that B is in the middle. The other is that C is in the middle. But just by the same argument, those cannot happen. That tells us that that lower branch cannot hold, and that leaves the top branch, which is A weakly majority preferred to C. Since A, B, and C were arbitrary alternatives, this means, or this implies, that the weak majority preference relation is transitive, and thus the strict majority preference relation is negatively transitive, i.e. it is a weak order. And that finishes the proof of the second part of this median voter theorem. It's a more general version of the median voter theorem. We see that the conclusions of the theorem are not as sharp as they are in the Euclidean case, because the majority preference relation does not have to coincide with the preference relation of the median voter. Nevertheless, the median voter's ideal point is a Condorcet winner, and the majority preference relation is a weak order. The very last thing that we can do is connect this to Arrow's impossibility theorem. Remember, as with the Euclidean case, there we argued that when we restrict the domain of possible preferences to the Euclidean profiles, that we actually had kind of an escape route from Arrow's theorem, right? Because majority rule satisfied Arrow's axioms, but didn't make anyone a dictator. The same holds here, and it's by the same logic, right? So let's assume that we're in the one-dimensional model, and let's assume that there is an odd number, and let me say that there's at least 3 individuals, okay? And the possible profiles are single-peaked with, and just for simplicity, we've been assuming distinct ideal points as well. Really, nothing rides on that. But then we, again, we've just shown with this sort of the single-peaked version of the median voter theorem, we've shown that the majority preference relation is always a ranking. So the majority social preference function satisfies rationality, and it always satisfies IA and Pareto. And and it doesn't make any individual a dictator, and so it satisfies this non-dictatorship axiom. Okay, so we have it's basically the same escape route as before, but it's just done with a more, a bigger domain of preferences. We don't really need the Euclidean assumption. Single-peakedness is enough for us to make this argument. Okay, so again, this one-dimensional structure, it simplifies this problem of preference aggregation. There's always a Condorcet winner. Majority of preferences are always a ranking. I suppose I could say one very last thing, which is here I've been assuming, that we're in this one-dimensional model and that the alternatives form a subset of the real line. Very last point is that the analysis that we've done, it's a little bit more general than that, because suppose that we have a set of alternatives that's not a subset of the real line, okay? All right, just think of them as abstract alternatives. It could be candidates in an election, just a set of projects that the group wants to do. Okay, just an abstract set of alternatives. So it's not, so we're not in the one-dimensional world anymore, but we can still sometimes have a profile of preferences and apply these results. Okay, so how would that work? So suppose we're given a profile. If the alternatives can be placed on the real line, now they might not literally be numbers, but suppose we just take these candidates and we put them on a line in some order, right? So given this preference profile, if we can place alternatives on the line in such a way that that we get single peak preferences, so in such a way that this profile is single peaked, well, then we can apply the median voter theorem on all these results we have. All right, so for example, suppose we have three alternatives, let's say, and three voters. Our alternatives, let's just call them A, B, and C, and they might not be numbers, okay? So they're not literally elements of this real line. But suppose we have a profile like this. Person 1 prefers A to B to C, and person 2 prefers about C to B to A, and person 3 prefers B to A to C. All right, so this is just an abstract model. Here's a preference profile. We can actually call this single peaked because, but I'll put it in quotes because I haven't been very formal about this, but this is a single peaked profile because we could just place these alternatives on the line. In fact, alphabetical order will do. And if we do that, this profile would then be single peaked according to the definition that we've given, okay? Right? Because each person has a single alternative at the top of their ranking, so they have an ideal point. Person 1 prefers A to B to C. So as we move to the right, things get worse for person 1. Person 2 prefers C to B to A. So as we move to the left, things get worse for person 2. And person 3 has B at the top, and then for this guy, you can't find 2 alternatives on one side of their ideal point, and so their preferences are single-peaked as well. So I know in this example there's an odd number of individuals, and they have single-peak preferences. So the median voter theorem that we proved applies. I know that person 3 is the median voter, so I know that their ideal point is a Condorcet winner, and I know that the majority preference relation is ranking. One more example of this, which we used before, was an example with 3 individuals and 4 alternatives. And there, in our earlier example, I just started with them on the line, but we don't have to start with them on the line. It could just be an abstract set of 4 alternatives, 4 candidates in an election. And in our example, we talked about a preference profile where the preferences were, there we are, so B, C, D, A, and C, B, A, D, and D, C, B, A. Okay, suppose I just say, all right, here's 4 alternatives, here's a preference profile. We can say, again, this profile is single-peaked. Because we could locate those on the line. Again, I tend to go with alphabetical order, but if we just put them in alphabetical order, this preference profile then would be single-peaked by our definition. Okay. But there are some preference profiles where you can't do that. The easiest example for me to pick is just the Condorcet paradox example. All right. Here, there's no way, I can't put these down in any order on the line that will make this single-peaked. So this preference profile is not single-peaked. All right. So this is just, it's just one little step more in the direction of generality. Sometimes we don't start with a one-dimensional structure, but given a preference profile, we can actually kind of back out a one-dimensional structure that allows us to apply the results from this one-dimensional model. Okay, so I've said a lot about majority voting, Euclidean preferences, single-peak preferences. You get the idea. This model has a lot of structure. We can get a lot out of it. It's a nice model to work with. It's been applied many, many times. So in future installments, we're going to be exploring that structure more, and we're going to move away from this kind of social choice framework where we're just aggregating preferences. We're going to impose more sort of institutional structure and think more about strategic aspects of politics using this model. Okay, so that's what's coming up, and I'll see you there.